Welcome to Industrial Problem Solving. My name is Dave Roysum. This is a continuation of a mini-series on troubleshooting web manufacturing and converting issues using best practices of traceability. Please see the 3 earlier clips if you have not already done so. Here we talk about the utility as well as the challenges of mapping a lane from the upstream end of a manufacturing machine all the way down through the parent roll and then through the daughter rolls onto a rewinder and possibly onto a customer. You may already use some form of lane mapping to do troubleshooting of internal rejects and customer complaints. We got a great start last time when we described best practices for roll ID numbers. But that does not tell us precisely where across the manufacturing machine's width where the trouble started. So here we will follow a lane of trouble from start to finish as it changes position and as it changes width through a manufacturing machine. A similar process can be used for downstream converting machines. We do this because most web processes are streaky. The fingerprint profile variation is mostly stable for hours to days. In many cases, such as with end rolls, the profile may be troubled since the day the machine started until the day it is shut down. Everyone gets so hung up on time. They fret over why one roll was good and the next not. They fret over why they went for days without trouble and then the product blew up at the customer. However, as I teach in my troubleshooting class, this can be a great way to get stuck. As I teach in my troubleshooting class, location may be more important than time for many problems. A root cause source with variability on the tending side cannot be responsible for a complaint on the drive side and vice versa. A narrow defect cannot be made by a wide source profile variation and vice versa. In previous clips, we showed how both roll ID numbers as well as time allow us to integrate different data sources. However, that's not always good enough or fine enough to be useful for troubleshooting. Here, we will be focusing much more narrowly. We want to find the responsible component of the complaint trouble for a daughter roll, or even finer, part of the width of a daughter roll. Many defects fall into this category of only showing up on a small part of the width of the machine. Let us take a closer look at one daughter roll with a complaint. Obviously, this is too small of a sample size to make any conclusions, so in the real world, we would be doing this 2 or 10 or 100 times. Note that the complaint roll was only one of 3 sets in the parent roll. The first question one might ask is, what changed with time within that parent roll to give this trouble on one roll and not the 2 previous rolls? Often the answer is, we didn't change a thing. However, if you thought about this just a bit more, you would have to admit everything changed. Variability is part and parcel of manufacturing. So here we could quickly get stuck listing parts that might move or might wear or might get contaminated. You could get stuck with control settings that might drift or adjustments that might have no readout. In those cases, variation is there, but beneath our radar. So in this clip, we are going to take an entirely different approach. That is, to identify the element that was variable across the width. Variable across the width is called profile. In this example, we find that the extruder or headbox or other web former was risky in one location, near the drive side edge. That location would show defects at sometimes, but not others. We can do much by merely knowing that the backside quarter point on the former was risky, even without ever knowing why one roll and not another misbehaved. So in this quite common example, we see that the complaint roll is the intersection of a lane of risk coming from one element with some element that also varies with time. These two elements could be the same or they could be different. For example, the former might have a lane-like profile variation, which also varies with time. Or the former might have a profile problem in that it is the customer's machine that owns the variability with time. Many of you will have learned how a web can be moved sideways in my award-winning and trademarked Web 101 class that has been taken by 5,000 students. The classic case is in-plane roller misalignment. Here, very approximately, the web will move about 1 millimeter sideways for a 1 millimeter roller misalignment, but only when it is in traction with that roller. You can get much more exact answers using the method in my Mechanics of Rollers book, or much more conveniently, the Wrinkle Predictor by Abbott App. However, there are many other ways the web can be moved sideways, as described in detail in Chapter 8 of my Web Handling Handbook. A machine can have perfect alignment via level and square as measured by your best optical instruments, and you could still have a ton of trouble. A machine could have perfect in-plane and out-of-plane alignment as the web sees it, and you could still have a ton of troubles. That is because there's an often neglected third alignment, that is, offset centerlines. Here we see 3 perfectly aligned modules, but the centerline of module 2 is offset towards the front. That makes the web appear to move to the back side of module 2 when in fact the web didn't move at all. Worse yet, we could take a perfectly centered trim, at least as how module 2 sees it, and the web appears yet in a different position. The same kind of challenge would be seen if you ran a perfectly centered guide position on module 2. In this example, the web position appears to be all over the place in modules 2 and 3, even though each is perfectly level and square. The web's width will obviously change when you trim. It will also change with many common processes such as tension, temperature, or moisture changes. Also curing and surface energy, spreading, and even winding as we see in this figure. Most of these are small and are calculatable or measurable if you take the time, but they do make for width bookkeeping challenges. Also note, when guiding on only one edge, width changes turn into position changes. Those 5,000 of you who have taken my award-winning and trademarked Web 101 class will have learned that spreading can be uniform, or it can have a profile, as can be modeled with some difficulty, or measured quite simply as gap width or lane separation after slitting. Here are the streamlines of a bowed roller, where spreading will be mostly uniform in the middle, but can be uneven at the edges if the web breaks loose there. About half of the spreader types are inherently non-uniform. The compliant cover and bent pipe and bowed rollers tend to spread better in the middle, and the edge pull and tenors clearly spread better at the edges. This topic was covered in more detail in one of my conference talks entitled Spreading and Traction and Drives. While these width changes are normally small, they can be enormous with certain operations like biaxial orientation, where the width change may be 200 or 300%. Formers, such as cast extruders and paper machines, have inherent width change profiles. Cast polymer extruders will neck in on the edges due to surface energy. This will cause the material to be heavier on the edges, baggier there, and skewed inward. On the wet end of the paper machines, however, the outward flow of the stock means that the ends tend to be lighter and skewed outward. The web can sometimes change width merely by going down through idler rollers. Worse yet, it may do that unevenly. This phenomenon is easiest to see on materials that have a grid on them, such as textiles and scrim, but it is a factor in many extensible webs, such as low modulus elastomers. Note how the edges of the material will tend to get heavier with this uneven necking. Finally, width changes with trim removal that may occur once or more on the maker, perhaps once again on the rewinder, and then perhaps finally again at the customer. Note that the amount taken on each edge may not necessarily be the same. We will have much more to say about not taking away enough trim in the next clip. Mapping the streamlines of a web through a process and through machines can be challenging. It may require some cleverness in measurement and bookkeeping, and possibly even some waste and delay. Yet you may need to do this if you are to ever trace lane-like defects to their source. Mapping is also required to tune automatic profile controls, such as seen on some extruders, wet ends of paper machines, and some profilable coaters. The mapping would include techniques such as following a defect lane. Unfortunately, that technique will only work if the defect were clearly visible all the way to the source and you were sure that there was not some invisible lane that preceded it. On some machines, you can bump a single lane on a former. This would include cast film bolts and paper machine slice lip actuators. In fact, this is how lanes can be mapped from the former to the weight or thickness scanners. This may be done manually or automatically. Finally, the brute force method is to mark the web somehow. Please, for safety's sake, avoid handheld markers. Instead, set up a chemically compatible marker such as an inkjet that can be remotely actuated. Thank you so very much for joining me in this problem-solving and problem-preventing process. In the next clip, we will discuss the troubles that can happen if you don't take enough trim. If you found anything interesting or useful, please consider supporting the work of this channel using the Patreon link below. Patreons are given special thank you gifts ranging from email help to a signed copy of my latest book, the must-have 500-page Web Handling Handbook. See you next time.